So this is the section on composite functions. And pre-calculus, you're probably wondering what's the big idea, what's the big reason for doing this. And you won't really fully appreciate this until you take calculus. So taking a function and making it into two other functions is critical for solving a lot of calculus problems. So if you have me for calculus, you'll see what's going on. Let me pause for just a second. Okay. So we're going to do problems somewhere here, 39 through 46, every one of them. So what they ask is for what is f of g of x and what is g of f of x. And it says find the domain of each function and each composite function. So 32, we have two functions. We have f of x is equal to the square root of 4 plus x, and g of x is equal to x squared. So the domain of each function, the domain of this function, well, the argument of the trig function has to be greater than 0. So x plus 4 has to be greater than or equal to 0, or x has to be greater than or equal to negative 4. For this second function, it can be all real numbers. So it would be negative. X is greater than negative infinity and less than positive infinity. So the composite function f of g of x, now they use this terminology. The usual is f of g of x. So what you do is you take the function, f function. Instead of having x, you plug in the g of x function. So instead of x, we get x squared plus 4. So the question is, what is the domain of this function? Well, you can see that the value of x can be taken on any real number, and the reason is because, for one thing, this equation is all real numbers, but if no matter whether I have a positive number or a negative number for x, it's going to get squared. So this squared thing is always going to be positive, and so that means that this argument is always going to be positive. So we can say for the composite function that the domain is all real numbers, even though this original f of x was more restrictive. Okay, continuing on, number 40, f of x equals the cube root of x minus 5, and g of x equals x cubed plus 1. So the difference between the square root and the cube root is you can, anytime you have an odd root, you can have negative numbers in here. So this can either be, the argument of odd roots can be either positive or negative. So it turns out that in this case, the domain for this is all real numbers. Likewise, for the cubic function, the domain is all real numbers. Now, when you do the composite function, f of g of x, what you do is you stick in, for x, you plug in x cubed plus 1. So we end up with the cube root of x cubed plus 1 minus 5. And you can simplify that down to x cubed minus 4. And for the same reason that this can be all real numbers. Therefore, the cube root can be all real numbers. The argument of a cube root can be all real numbers. Same thing applies here. So x cubed, the actual range of this function, is also all real numbers. It's going to look something, it's going to be like that. So it goes from negative infinity to positive infinity as far as the range is concerned. So this can be positive or negative, which is fine. So anyway, that's the composite function. And the domain is, again, all real numbers. Okay, 40. So there you got f of x equals x squared plus 1. G of x equals the square root of g of x, not f of x. G of x equals the square root of x. Okay, so the domain here, again, is all real numbers. Polynomials, you can be all real numbers. Here, x has to be greater than or equal to 0. So the composite function f of g of x, so for x squared, for x in this expression, we put in the square root of x. So you get the square root of x squared plus 1. And so if you square that, you'll get x plus 1. Now the question is, here x has to be greater than x has to be greater than 0. So even though when I multiply this thing out, I get x, I can't just look at this equation and say that the domain is all real numbers, because the previous step, before I simplified it, it had the restriction that x had to be greater than or equal to 0. So you always look at it at this point, not at the final point. And I just realized that I was also supposed to do g of f of x, so let's do that. So we go back here, g of f of x. So if we plug in this into there, you'll have the quantity, the square root of 4 plus x, quantity squared. And you could simplify that down to x plus 1, and that's okay to do that. But you have to go to this previous step to look at what is the domain as far as this pre-simplified step. So in this case, x plus 4 has to be greater than or equal to 0, so that the argument of the square root function is positive, so you get x is greater than or equal to negative 4. So that's the domain of that one. And I'm just, I'm just checking my answers here while I go along. Make sure I'm not making any mistakes. So let's see, 39. Yeah, okay, so we're good there. Let's go to 40 now. So we need to do g of f of x. So if we do that, we get g of f of x. So what I'm doing is I'm going to plug that into here. So you have the quantity, the cube root of x minus 5, quantity cubed plus 1, and something cubed to the third power is just the argument. And so that simplifies down to x minus 4. So that's f of g of x. But again, going back here, you look at the domain, and the domain was from negative infinity to positive infinity, so in this case, it's still all real numbers. It was right, it's true here and it's true there. Okay, and so we still need to do g of f of x here. So we take this and plug it in there. So we get the square root of x squared plus 1. Now you can't simplify that any. And what we need is for the argument, so I haven't simplified anything, and I really can't simplify it any further than this anyway. So you can see that no matter what x value is, from negative infinity to positive infinity, I'm always going to end up with a positive number here, which means I'm going to have a positive number plus 1, which is going to be positive. So in this case, the domain for x for the composite function is all real numbers. And let me just check that. So it says all real numbers. Okay, I think I know what I'm doing here. Okay, 42. So we have f of x is x to the 2/3, and g of x is x to the 6th. Okay, so what is x to the 2/3? It's going to be the cube root of x squared. Think of it like that, or you can think of it as the cube root of x quantity squared. So those are two ways of representing that. This one's just what it is. So for g of x, I can take any value. X can take on any value, and there's no restriction. Now, if I look at it from this perspective, if I square something, it's going to become positive, and then I can take the cube root of it. Or here, I can take the cube root of something, and that can be any value, because you can always take the cube root of a positive or negative number. And then if I square it, it becomes positive. So in both cases, this gives you a positive result, which means the range is from 0 to positive infinity. But we also can say that the domain of that function, it can take any value, and we can evaluate that. So then we have the two composite functions, f of g of x. So that's x to the 6th to the 2/3 power. Now again, I haven't simplified it yet. So I look at this form, and I can look at the domain for that. And you can see that this was all real numbers, because this is always going to be positive with an even exponent. And if this is positive, then we can evaluate it at any value. So this is all real numbers. And if we simplify it down, what you would do is you'd multiply the exponents together, and you'd have 6 times 2/3, which is 4. So that would be the function we would use, simplified. And then you have g of f of x, which is going to be this plugged into there. So it's x to the 2/3 power to the 6th power. And it simplifies down to the same thing, x to the 4th. And again, this x can take on any value in here, which will give you the positive. Well, it'll actually end up always giving you a positive number. And you can always take a positive number to the 6th power. So in this case, the domain for all cases is all real numbers. And we'll just check that out. Yep. It simplifies both cases to x to the 4th. Okay, then we got 43. F of x equals the absolute value of x. G of x equals x plus 6. So you can take the absolute value of any number. If it's negative, it becomes positive. If it's positive, it stays positive. And this is just a linear equation, so it also is all real numbers. Then you have f of g of x. So we plug that into here. So you get the absolute value of x plus 6, which again, all real numbers is the domain. You can have both positive and negative x values. And then you have g of f of x, which is going to be the absolute value of x plus the absolute value of x plus 6. And again, there's no restriction on the x values for the absolute value function. So it looks like they're all of them are all real numbers. So this is 43. Yep, that's good. Okay, next one. Make sure I'm not going too far here. Okay, I've got 3 more. 44 is f of x equals the absolute value of x minus 4, and g of x equals 3 minus x. So just for the same reason as this, x can take on any value because you can take the absolute value of both positive and negative numbers. So this is all real numbers. This is just a linear equation. That's always got all real numbers. And then we have f of g of x. So what we do is we plug that into here. So you get x, 3 minus x. Instead of x, we put in this other function. So you get 3 minus x minus 4. And that simplifies down to negative x minus 1. And again, all real numbers are allowed in here because we can take the absolute value of both positive and negative numbers. And then you have g of f of x. So that's the other way around. We're going to plug that over here. So you get 3 minus, instead of x, you put in absolute value of 4 minus x. And for the same reason, you can have any value of x. Of course, the ranges are different, but they're not asking for the ranges. They're just asking for the domain, possible place values. Okay, f of x is 1 over x. G of x is x plus 3. So rational functions, the only time this doesn't work is if the denominator goes to 0. So what we can say is that the domain is such that you can go all the way from negative infinity to 0 and all the way from 0 to positive infinity, but not including 0. The second one is just a linear equation, so that works. So f of g of x is 1 over, instead of 1 over x, it's 1 over x plus 3. So again, for this thing to, the only time this is going to be undefined is when the denominator equals 0. So you find x equals negative 3. So the domain in this case is from negative infinity to negative 3, and from negative 3 to positive infinity, but not including negative 3. Or you could say all real numbers except negative 3. That's another way. All real numbers except x equals negative 3. And then g of f of x, you're going to plug that over here. So that becomes 1 over x plus 3. So the only time this function is not evaluate, that's a big word. The only time you can't evaluate this function is when the denominator of the first term is 0. So this has the same domain as 1 over x. So it's good from negative infinity to 0, and from 0 to positive infinity, or you could say all real numbers except x equals negative 3. Okay, check out the answer here. It says the domain of f of x and g of f of x are all real numbers except x equals 0. Yep. The domain of g is all real numbers, that's what I said. And the domain of f of g of x is all real numbers except negative 3. Here's the last one of the group, 46. So you have f of x equals 3 over x squared minus 1. G of x equals x plus 1. So the second one's easy. That's a linear term. So that's a linear expression. It's all real numbers. Here, again, what we have to have is that the denominator does not equal 0. So we find out the values for when x equals 0. So what you get is x is minus 1 or plus 1. So those are the two values of x. And therefore, the way you do it, you could say all real numbers except x equals negative 1 and x equals positive 1. So that's the domain of this one. Okay, now our composite function, f of g of x. So what we do is we put g of x in for x. So we get 3 over x plus 1 squared minus 1. And we can multiply out the denominator. Well, actually, we'll multiply it out first. So you'll get x squared plus 2x plus 1 minus 1. So multiplying this out using full, you get that, and you can then cancel the last term out. So you get x squared minus plus 2x. And so we could factor out an x in the denominator. So you get x times x plus 2. So there are two values, x equals 0 and x equals negative 2, which causes the denominator to go to 0. So for this case, it's all real numbers except when x equals 0 and x equals negative 2. And you kind of check that out. If you put 0 in here, you'll get 1 squared, which is 1 minus 1, which is 0. And if you put negative 2 in, you'll get negative 2 will give you negative 2 plus 1, which is negative 1. Negative 1 squared is positive 1. Positive 1 minus, so that makes sense. And then you have g of f of x. So what we do is we plug that into here. So instead of x, we'll have 3 divided by x squared minus 1 plus 1. Now we could simplify that and combine these two terms, but to answer the domain, it's going to be the same domain as this because that's what causes, this is always 1, so that's always a number. The first term is going to be undefined when the denominator equals 0. So in this second case, we can say all real numbers except x equals 0 and x equals negative 2. Okay, check it out here. And that's correct. Okay, I've got a few more here. What is it? 59, 60, and 63. So let me write those down. 60, 63. Okay, 59. The square concrete foundation prepared as the base for a cylindrical tank. The radius r of the tank is a function of the length of the side x of the square. So what we have is we have this square, and on this square base we put a circular tank of some kind. So something like that. I think I gotta see if I can get this thing centered. There we go. Okay. So this side is x, and the radius of the circle is that. So you can see that r is equal to x over 2. Write the area of the circular base of the tank as a function of the radius. So the area as a function of radius is just the area of a circle, which is pi r squared. And then it says find and interpret a of r of x. So this is like my f of x, and this is like my g of x. So what that allows me to do is to figure out what the area of the tank is based on the dimensions of the square thing. So I'd have pi, instead of r, I'd put in x over 2, and then I'd square it. And so I would get pi x squared over 4. So that's what the area of the circle is given the dimensions of the base. Okay, second one. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius in feet of the outer ripple is r of t is 0.6 t, where t is the time in seconds. The area of the circle given by the function pi r squared. Find and interpret a of r of t. So we have r of t is 0.6 t. A of r is pi r squared. So what we want, if we want to find what a of t is, what's the area as a function of time, we'll do a of r of t. So the area is a function of radius, but radius is a function of time. So we just take pi, but instead of r squared, we put in the result here, which would be 0.6 t, and we square that. And so if you square 0.6, you'll get 0.36. You get 0.36 pi t squared. So that's the area as a function of time. That's the area as a function of radius. So it's a composite function that, and in this case, r or t would have to be greater than 0. And therefore, r is greater than 0, which means that the area is always greater than 0. And then finally, number 63, it says, think about. You are sales representative for an automobile manufacturer. You are paid an annual salary plus a bonus of 3% of your sales over $50,000. Consider the two functions. Okay, so f of x is x over, so that is your salary over $500,000. And g of x is the 3% bonus. So to find your bonus, you would do g of f of x, because you're taking 3% of your salary over $500,000. So it would be 0.03 times x minus 500,000. So that's your bonus. And it says, which of the following represents your bonus? Okay, we just answered the question. It's g of f of x instead of f of g of x. So the way you'd actually figure out your salary, well, yeah, your total salary would be equal to some base amount plus your salary, your sales over $500,000. So, of course, if you sold less than $500,000, you wouldn't get stuff subtracted from your salary. So it'd be kind of like they don't ask you actually for this, but you know, I guess if X is less than 500,000, then the salary is your base amount. If X is greater than 500,000, then your salary would be calculated as such. Okay, let's see what it says in the book. G of f of x represents 3% of the amount over 500,000. So they agree that it's G of f of x.